Hey everyone, so we're going to be starting the next topic in this class. It's all about Boltzmann distribution and the Helmholtz free energy. So we talked about entropy and the concept based off of that. So we're going to take it one step further and kind of figure some more things out based off of what we have so far. All right, so there's this thing called a Boltzmann factor that ends up playing a part in this whole topic of thermodynamics. Um, Now, in order to come up with this Boltzmann factor, what we're going to do is we're going to consider a system. And this system is going to be in some sort of thermal equilibrium with a large reservoir. So remember, large reservoirs usually are things that are just so massive that we can consider them as maintaining their temperature state. Um, and when we say thermal equilibrium, remember that means that there's only heat being transferred. Both of them are separated. They're in a closed system, so only energy can transfer. And what that also is trying to refer to is that this system is going to have a very consistent temperature throughout. Now, the total energy is also going to be constant because between the system and the reservoir, it is isolated, so there's not going to be any energy lost to the environment. Any energy that the reservoir has, uh, whether it gains or loses it, is going to go into the system. Now, what we're going to do is we're going to actually define the energy within the system as being this epsilon, and that means that we can rewrite this for the energy of the reservoir as U naught minus the system's energy. We're doing this so that when we start doing some of the calculations, everything is going to be based off of this energy. We're not going to have two variables anymore. We're going to have one variable because U naught is going to be constant no matter what. All right. So by doing this, what this is going to tell us is that because we're actually specifying the state of the system, and that we're saying that it can pretty much only have one possible state, then our multiplicity function based off of the energies, normally it would be the product of the two multiplicity functions, the number of possible states in the reservoir times the number of possible states in the system. Well, this just becomes one because we're identifying which specific state we're looking for. So the multiplicity function just becomes that of the reservoir. Now, as we know, the because each state is going to be equally likely, we know that the probability of finding any particular state is going to be some factor times the number of possible states. So, and we're setting it so that when we sum across all the energy states, the probability should add up to 1. Now, we're going to use something called a Taylor expansion for the entropy. So, as we know, entropy is defined as the ln of the multiplicity function. We can use the Taylor expansion so that it looks something like this. Every other term we're not going to have to worry too much about. All we care about pretty much are these first two terms. Um, so when we do this, setting these equal to each other, this just becomes we actually know what this is defined as. It's 1 over tau. That's what we talked about in the last video. So getting rid of the ln's by raising everything to the e, we end up getting this function for the multiplicity function on the reservoir. So this ends up being the multiplicity based off of the constant energy, and then we have this variable term right here. So that's kind of one of the reasons why we're doing this, so that we have a more, I guess you could say, manageable variable term. See, originally, if we just dealt with this by itself, then this whole thing is a variable, but now we're limiting it to this e function. So from there, we can actually see that this term here is what we're going to call the Boltzmann factor, because the probability is going to be based off of this factor right here. Because as we know, the probability is proportional to the number of states. The number of multiplicity states. So because this is proportional to this factor, then the probability also has to be proportional to that. Now, why we're doing this is because I know that's one of the big things with a lot of this stuff is the big question of, well, why are we doing this? What is the whole point? The main point for this is for the case where we have two states for the system, and we want to try to figure out the probability. We don't need to know these numbers because what we can do is we can come up with a ratio of the probabilities, and that way we know that it's going to be the ratio of these two factor terms that we care about. Because if we go back, I'm not going to go back, but if we go back to the equation that we had for probability, it was a times this multiplicity times this. So the a term is constant for every state. This term is constant for every state. So the ratio would simplify to just being a difference of, or a ratio of these e factors, the Boltzmann factors. Now, what we can do actually is we can take it one step further, and we could set state 2 so that it has zero energy. And that's going to make our probability a lot easier to find. All right. So what we can actually do is we could kind of take that definition of the fact that we're doing a ratio of the probabilities and pretty much say that the divided by the sum or the total probability. So that would actually mean that the probability of finding the system at one specific energy state would be equal to the Boltzmann factor at that specific state divided by the sum of all the Boltzmann factors over all the states. Uh, and this is what we're actually defining as the partition function. So this bottom part, that's what we're going to call the partition function. And it's going to be used a decent amount. You can think of the partition function as kind of being like the multiplicity function, because it's going to tell us pretty much the number of complete states, just like how we had the other equation for probability where it was the number of states, the number of possible states for one specific half spin divided by all of the possible states. It's the same thing, except now instead of talking about half spins, it's focusing on energy states. So that's one way to think about this, is that it's the partition function is sort of like the multiplicity function, except more of as like a total of states rather than for one specific state or another. So we're going to define the partition function with the symbol z, and it's going to look like this: the sum of all the energy states. So that means our probability equation can actually be rewritten like this. Now we're going to be doing a whole bunch of questions. In fact, I think for the most part, the rest of this video is just going to be practicing using the partition function, seeing kind of what we're going to do. And then the second half of this video, actually, I don't know if it's this video, in the second video, we're gonna take this partition function and see what we can find with it. All right, so we can actually kind of reuse this with some of the things that we know about our definition for average. in particular the average energy. So if you remember, we define the average of anything as being the weighted average, or the weighted sum, I should say, of every single possible state. So that's what we're going to do here. We're actually going to define the average energy as just a capital U. You'll see that it kind of goes back and forth. So the average energy is just the sum of all the energy states times the probability. Using our probability equation for the energy states, it's the Boltzmann factor divided by the partition function. So the partition function, because it's already a sum, and it's also a single value, it can be pulled out of the summation, and we end up getting this. Now, because of the fact that the partition function is the sum of e to the negative epsilon s over tau, we can actually see with a little bit of calculus that there is a relationship between these two. In fact, if I take the derivative of this term, I would get something that looks something like this. So this can be rewritten one step further like this. Tau squared, the partial derivative of ln z divided by delta tau. If you want, you can actually test this out yourself, and you will see that you'll get this equation. All right, so all this stuff is going to pretty much play a part, as I said, later on, and you're going to be seeing a lot of these terms popping up over and over again. In fact, the partition function gets used a lot, and then later on we're going to talk about something else that's very similar to the partition function, but a little bit more general. All right, so here what I want you to do is show that the partition function is the product of the individual partition function. So pause video, work on yourself, and we'll go over in a second. All right, so what we're going to do is we know that the partition function is equal to this. It's the summation of the Boltzmann constant across all the states. So that means that if I'm taking the partition function of a sum of two systems, then that's just going to be a double sum, just like that. So then what I'm going to do, I can separate them out. So when I separate them, because the thing is, the e to the epsilon s1 doesn't change based off of this. So I can actually pull this out into the summation of across system 1 and the summation across system 2. Well, this is just the partition function of system 1, and this is the partition function of system 2. And that's it. Hey, easy peasy lemon squeezy. All right, here's the next question. You can pause the video, work on this, and we'll go over it in a second. All right, so they're giving us this information. So they're telling us that we have one particle that can only be in one of two states, either zero energy or epsilon energy. And they're also telling us that the temperature is constant. That's all this line is telling us. So to find the energy, we're going to use the partition function. Now this is what we're doing. So we know that we have one particle, and it could be in either states, 0 or epsilon. So there's only two possible states, 0 and epsilon. So all we do is just simplify this, and we get our equation. This is our partition function. Going back to the equation we have for the average energy, remember it was the sum of epsilon s times the Boltzmann factor divided by z. So what we can do is just plug in, once again, 0 for one energy state and epsilon for the other. So there's two states, state 1 and state 2. This is 0 energy and this was epsilon energy, and we end up getting this. Now this simplifies as being Yeah, pretty much that. So this is becomes 0. I can actually bring this to the bottom because e to the negative epsilon brings it to the denominator, multiply it through across. So if you want, you can write it as either this form or this form. I would accept either or because they're both roughly the same relation. So I just want to go back that this is kind of what you're going to be doing the partition function as, and this is how you're going to be using the Boltzmann factor. They're going to tell you about how many, like the different states that are available. Usually it's going to be a number less than 4, I would say, and you're pretty much going to write it out. Um, yeah, and that's pretty much it. Now to find the heat capacity, well, remember that heat capacity is defined as tau times the partial derivative of the entropy, or it could uh, be defined as the partial derivative of the energy with respect to temperature. So if we take our equation that we just got for the energy and take the partial derivative of it with respect to tau, we end up getting this jumbled mess right here. You're going to have to play around with this as best you can. Um, you might want to do some sort of like a U substitution if you're having trouble with it. But basically, it's that whole idea that when you take this, you have to take the derivative of what's inside and then subtract 1 from the exponent, that whole thing. It might make it a lot easier to rewrite this as e to the e to the epsilon over tau plus 1 to the negative power, the negative 1 power. But once you get this, then you just simplify again as best you can. But you should end up getting something like this. I actually want to quickly go back. The only benefit to actually simplifying the energy equation was more for this state. When you do end up having to take derivatives, it becomes easier when you have less items involved. All right, here's another question. So we're going back to that Einstein solid. So pause video, work on the stuff, and we'll go over in a second. Okay, so they're giving us the multiplicity function. They want the energy as a function of temperature, and they're actually giving us the energy, so we know where we're supposed to end at. So this is going to make life pretty nice for us. All right. So based off of this, we know that the entropy is found by taking the ln of this term, which gives us this q to the ln n over q plus 1. Um, so the energy is going to be equal to q, which is the number of energy units. Remember, that's what q was defined as, like how many energy units are available. And then this epsilon is essentially just the value of the energy unit. So from here, I can rewrite this so that I'm getting rid of the q's, and it's now going to be in terms of this epsilon. So we have the epsilon here and the epsilon over here. Then I could separate the ln terms. So now, again, once again, I just have the epsilon terms here and here. Now, then remember that we can relate because they want us as a function of temperature. So we can find the energy by taking the partial derivative of the entropy with respect to the energy. Do that, and we're basically taking the derivative of this term and taking the derivative of this term. So you have to use the whole chain rule here, but we end up getting this. This whole long term ends up simplifying simply to just this part, because what's going to end up happening is these are going to cancel out, and we're going to have a minus 1 that can be brought back into here. So these are the only terms that remain. So we get this, And then from here, we can actually already see that we have all the terms that we have up here. We just need to write them in the proper way. So multiply the epsilon over, raise both parts to the e, to the e, and then you could do a flip of the u over to here and this over to there, and we get exactly what they gave us before. All right, here's the next question. Pause the video, work on this stuff, and we'll go over in a second. All right, so here they want us to find the heat capacity. So this goes back to pretty much the same equation that we did last time. The fact that we're going to be taking the energy equation and taking the partial derivative with respect to temperature. So it's pretty easy. The temperature is up here, so that's a pretty straightforward derivative to take. And we just kind of simplify, clean it up a bit, and we get this. All right, so going back to the partition function, pause the video, work on this stuff, and we'll go over in a second. All right, so this is a zipper question. So once again, we have two states. They could either be in energy 0 or energy epsilon. And what they're actually saying is that if we know that up to a certain state S is open, so they have energy epsilon, then everything to the left of that also has epsilon. And that everything else would end up having an energy of 0. So once again, we actually know what we're supposed to end up getting for the partition function. So we're just going to go back and try to see how we can kind of fool around with this to get to this equation. So we know that the partition function is going to look something like this. Now, the reason why I put the S epsilon here is because we know that once we get to a certain state S, each one's gonna end up having an energy epsilon, so it's gonna be in total S epsilon. All right, so here, what we're gonna do is we're gonna do an X substitution. So we're gonna replace the e to the negative epsilon over tau with X. So this is going to be a sum of x to the s power. Now this has a very common simplification. It's defined, if we're going from s equals 0 to n, then it's defined as this. 1 minus x to the n plus 1 over 1 minus x. Once we have this, then we can take this function and put it back in for x, and we get exactly what they gave us. Now, if you're thinking, how is they supposed to know to do that? Well, that's one of the things about this class is that the first time you're seeing a lot of these things, you really shouldn't have an immediate reaction of, oh, that's what I was supposed to do. It's not until we go over it and you start to actually see some of the tricks that we're doing. One thing, though, is that as we continue, you should start to notice some of these tricks occurring over and over again. Like, for example, this idea of doing this and then replacing this entire thing with x so that we can figure out how it gets simplified. That trick gets used a lot in this class. It's a pretty common calculus. I actually can't even remember what the levels of math are anymore. But it is a very common trick to do with infinite series. So just be aware of that it's still kind of the beginning, especially the first video of each of these topics. So you may not immediately know it before I go over it, but after I go over it, you should kind of be able to recognize the patterns later on, like on homeworks and on future questions. All right, so continuing on with that, here's the next part. Pause video, work on the stuff. We'll go over in a second. All right, so here we're going to try to figure out the average number of open links. So as we know, the average number is just doing the sum of the the number of states, the number of links that are open, because that's what S is being used for here, times the Boltzmann factor divided by the partition function. Once again, we're replacing the e to the negative epsilon over tau with x so that we get this. Remember, the partition function is not really part of the summation. So it gets pulled out of the summation, and then we're left with this part. Um, and this actually is also something that we can simplify because remember, partition functions got the summation. Um, and this kind of looks kind of what we did, like we did before, where we can just say, oh, well, this is just the partial derivative of ln z. So as I've said before, you kind of want to try to keep using a lot of the tricks that we've done before. And this was something that we did right after I brought up the partition function and I was discussing, I believe, the average energy. So, you know, these, like I said, these tricks do pop up regularly. From here, since we know what the partition function is, we could just plug that in. And then what we can do is actually just take the partial derivative with respect to x. Now, because they told us that epsilon is much greater than tau, what that means is that this term for x, where is it? Here, this term for x is pretty much very, very small. It's, you know, something that we don't really have to worry about. So when we have something like this, x to the n plus 1, where n is going to be assumed to be a huge number, um, a super small number raised to a very large power is essentially zero. So that's the importance of this. It's going to tell us which things we can kind of disregard. So this gets dropped out and we're left with this. Now, even though we're saying that x is very small, because this isn't raised to any power, we're just going to leave it in. So then from here, we can actually take the partial derivative of this. This is just 0. And then we have this term, which just ends up being 1 over x minus 1, getting rid of that negative. So this is what it simplifies to, and then we could just plug that e to the whatever back in for x, and we get this for the average number of links that are open. All right, and we're just going to leave the video at that. We'll derive some more equations using the partition function, and we're going to see how it relates to something called Helmholtz free energy. If you have any questions, please let me know. Otherwise, I'll see you later.